Okay, hey, welcome back to the John Baez Category Theory Seminar. As you may have noticed, I'm not John Baez. So, my name is Franciscus, and I'm one of John's grad student research lackeys. And he asked me today to talk about some relevant things that we've been talking about since he's off in Canada for one of the conferences that he is constantly running away from this campus to go to. So yeah, I'm going to talk about composing spans and get a little into bicategories and what is a bicategory. Okay, so last week we were looking at this situation. I forget exactly what letters we were using, but just use letters like these. And I think the arrows were going this way. So in my research, the arrows actually go the other way, and I consider spans. These are what are called cospans. And they go this way because we were thinking about electric circuit kind of diagrams where we'd have a graph of stuff with some electrical gear attached, and we have some nodes at the top and bottom that are inputs and outputs. If we call this set of nodes A, and this set of nodes B, and this entire circuit X, then we have a couple of inclusion arrows. So you can just think of A and B sitting inside of X. Okay, so we asked how to compose things like these. So if we have this situation, B here is basically acting as both a set of outputs of one graph and inputs of the next graph. And we want to glue these two graphs together, right? And we saw that the answer to how to glue two things together in a really highfalutin categorical language is this thing called the Pushout. So I'll write it as x times y, and it's happening over B here. Okay, and this Pushout guy has this universal property that if you have any other guy trying to act like a Pushout, we called it a competitor. And if you have a couple of arrows going to your competitor like that, such that this commutes, right? So then it's going to give you a unique arrow from the Pushout to the competitor that makes the entire thing commute. Was it going this way or was it going the other way? Oh. Now I'm starting to feel like it was going the other way. Suddenly I'm having a bad feeling. Maybe it was going the other way. That's right. Okay, this is good? Okay. So, yeah, this is how we'll compose in our category. So we're trying to set up a category where the objects are, well, they're just objects. Call them things like A, B, C, etc. But then the morphisms are cospans, which are these kind of simple diagrams. Okay, so what do we need to have a category? There's just a few axioms. Each object needs to have, well, maybe I'll come to that next. So first of all, composition of morphisms has to always be possible when they're compatible. So we compose two compatible cospans. So this is a way to notate this cospan right here. X with subscript A on the left, subscript B on the right. So if we've got a couple of compatible cospans like this, we compose them with the pushout. Now, there's a little subtlety here. I almost wrote the pushout because I'm used to doing that, but in fact, there's not exactly one unique pushout, right? So this is an issue that came up toward the end last time. So we define AXB circle BYC to be a pushout like this, happening over the middle compatible guy B. But there's not just one pushout. But we did see that because of the universal property of pushouts, any two pushouts are isomorphic in a unique way. So we can use any pushout since two different pushouts are isomorphic in a unique way. They say canonically isomorphic. Okay, so define our composition this way. Now, what else do we need for a category? Well, we need composition to be associative. Right? So for this, we need to look at a triple of cospans. Like this. And we need that compose the first two guys first, and then the last guy. That needs to be the same as the first guy composed with the second two guys done first. So why should that actually happen here? If you think about what this composition means, it's pushouts. So the first one, or the left side, is the following. So you're taking the push out of x and y over v first. It's here. And then you notice that there's a common compatible node at the bottom here, C, for these two objects here. So C can go all the way up to this pushout, or it can go to Z here. So because of that, we can form another pushout, which is that of these two guys over C. So that's what this left side here is. the other hand, the right side. It's got the same base diagram. And in this one, you take this push out over here. Over C. And then you see that B is a common node for this guy and for this guy, so you can form the push out over B of X and push out of Y and Z. So these two things, if we're to have a real category like this, are supposed to be actually equal. So the rule for composition in a category is that it has to be a full-on equal sign. So the fact of the matter is these two iterated push-outs are not equal with an equal sign, but they are isomorphic. So there's a couple ways we can get around this issue and give ourselves a, well, there's one way that we can get around the issue and have a category. Or there's another approach where instead of getting a strict category, you build a looser kind of thing called a bicategory instead. So I'll talk about the second thing in the second half, but for now, the way we can get away with this is declare the composition of pushouts in our category of cosines to be an isomorphism class. So by doing this, it relaxes everything. The point is, and I probably, I'm not going to prove this, but I'll talk a little bit about why. So the fact is, this iterated pushout is canonically isomorphic to iterating the other way. And in fact, both of these iterated pushouts are basically the same as what's called the limit of this bottom bit that we started out with. So they're both canonically isomorphic. Actually, I should say the colimit because we're working with cospans. So they're both the colimit of this base diagram. So I'll explain what colimits are, but are there any questions on anything I've said so far, these issues? Okay, so what's a colimit in general? This will just be a quick digression, and actually we need to talk about limits and colimits and stuff when we get to the bicategory of cospans. So yeah, there's no way around it really. Okay, so the easiest way to think about limits and colimits, I think, there are different ways to phrase the definition. But universal cones and cocones, I think, is the simplest. So think of it as a universal cocone for a given diagram. Well, what is a universal cocone? I'll explain. So first, a cocone for a diagram D, so fancy D, is an object together with arrows from every object down in your diagram let me call the object C. So with arrows from every object in your diagram to C, such that any two ways to get from an object in D to C are equal. Okay, so let's see an example. So you have some random diagram here. Something like this. Say this is D. Then a colimit, or sorry, not a colimit yet, but a cocone is going to be a new object here, C, and arrows from every object in D to C. So that any two ways to get from an object down in D up to C are equal. So, for example, we could go from this object directly up to C here, or we could first go over to this object and then up to C. And that makes this triangle here, and that has to commute. So, all blue triangles. So that's what a cocone is. A cone is exactly the same thing, except the arrows go from the cone down to the diagram instead of the other way around. And again, it makes all the triangles commute. So now, what does it mean for a cocone to be universal? Well, it's the business with the competitor. So, a universal cocone, sorry, C, has the property that given any other cocone Q of the same diagram, there's a unique arrow from C to Q that makes all new triangles. So, if we bring in a competitor, another cocone Q over here, that means there's going to be, let's see, is there a red? Let me make it red. Ah, it's dead. Okay, well, if we have a competitor here, that means we've got all these arrows. And if this guy's universal, it means that there's a special unique arrow going from C to Q that makes all the new triangles commute. What do I mean by a new triangle? Well, for example, basically any triangle that uses this new unique arrow that we've just drawn. So from this guy, we can go up to C and then over to Q with the unique arrow, or directly to Q. That has to commute. So all the new triangles. Okay, so the idea is a universal cocone is in some sense the primordial cocone, because if you have any other one, then you could just as well just go to this first one and then to that one with the unique arrow. That's the idea. Okay, so yeah, now you know what a colimit is. It's a universal cocone. And I'll just on the side say a limit of a diagram D is a universal cone. Where the definition is just like universal cocone, but with all arrows reversed. Okay, so I said that these two iterated push-out things are really just the same up to a canonical isomorphism as a limit. So, sorry, it's a colimit. I'm sure I'll keep making this mistake all day long. So what sort of thing would the colimit of this picture look like? Well, it's going to be, uh-oh, I've already used C. Okay, let me call it L. Even though L usually stands for limit, it'll be the colimit here. So the colimit, what we've just seen, needs to have arrows from every guy down here up to id.
Franciscus.
Yep. Oh, thanks. Yeah. Yeah, that is better, thanks. Okay, so the limit has to have arrows from every guy down in our base diagram up to it. And all these triangles have to commute. Now, I say we actually don't need to draw in these blue arrows coming from A, B, C, and D up to L. Anybody see why that is?
So you might as well just go from A to X.
Yeah, exactly. So this way of going from A to L makes a triangle with A to X to L, and those have to commute by definition, right? So you might as well just use this one, yeah. Same for all the other guys. So we typically don't draw in those lower level ones. And so, yeah, this has the property that all of these guys commute. Well, there's really just two triangles here. This one from B, and this one from C. And actually, they're not triangles, but squares. But anyway, the definition still holds. Okay, so let's see if we can see that this thing here does the same role as those iterated pushouts. So we also have push out here. X and Y over V, and push out. But that thing with Z. So that was one half of our composition associativity. The other half was we had this push out, Y and Z over C, and we could take that with X. Okay, so it starts to get a little bit messy. But here's the claim. X times Y times Z, I shouldn't say times, but push out. And X push out Y, push out Z. Are both universal cocones on the base diagram. The base diagram being this thing. So they both do the job of being a limit. I mean the Colimit. They're both canonically isomorphic to the Colimit. Okay, and therefore, if we define in our category composition of cospans to be these canonical isomorphism classes, then we can treat them as the same, really. We get associativity as desired. Okay, but I haven't actually proved that they're both universal cocones for this diagram. I do it in this paper that I'm working on with John, but I think it's a little long to get into all of the nitty-gritty details of it today. But maybe I'll just write up here on the side a couple of references. So a good starting point for all of this stuff is a brief introduction to bicategories. By Luis Barbosa. You can find this on the archive, and he gives the example of a bicategory of spans, so not cospans, but it's pretty much all exactly the same, just with the arrows flipped around. In my paper, so John, I think, emailed everybody on the mailing list a draft of this. It's not quite ready yet. It's going to be called Building the Bicategory Span 2 of C. Okay, so that's how we get associativity. And we're almost done to see that we have full-on category. What's the last axiom we haven't checked off? Identities, right? Yeah, that's it. So, still need to check. Identities, exist and work. Okay, so an identity arrow goes from a given object to itself. But we're dealing with a category where the arrows are cospans. So what should we fill in here, and what should the two arrows be for it to be an identity cospan? It's the only thing that really makes sense. There's not that many things in sight that we can play with. Yep, A. Yeah, let's put A there. And what arrows? So remember, there's a kind of background context here where these objects like A, B, C, etc., and the arrows going between them are coming from some background category. So we have some category. So because we have some category, we have an identity on A. So that's the arrows we use. Okay, so this will be the identity on A. This cospan. So we need to check that it actually works the way identities are meant to work. So let's say we've got, oops, switch to spans. So let's say we compose the identity on A with some other random cospan. We're supposed to get X back, right? So we should have that this identity cospan composed with any other cospan equals the second one to really be a category. So the way we compose, remember, is with this thing called Pushout. And the claim is that this Pushout that I'm currently writing is A Pushout with X over A is really just as good as, so I'll put an isomorphism here, is really just as good as putting X by itself. Okay. So let's try to see this. Okay, so what can we say about this Pushout here? And remember, we know that this is just the identity arrow from A to itself. Anybody have a suggestion? I should emphasize that there's a canonically unique way that these two things are isomorphic. So basically the idea is to treat them as competitors to each other and see that they do the same job. So let's focus on the right side. Okay, so this is the identity. Now, I'm claiming that X works as a pushout for this whole diagram. So X has to come with a pair of arrows going up to it that are drawn here. What do you guys think this arrow from X to X should be? Yeah, that's right. Identity on X. Okay, and how about this arrow here from A to X? Well, we don't have a name for that, but I say it's the same as something else that's nearby. This other arrow from A to X. Yeah, so let's call this thing F for the moment. Then it turns out this needs to be that same F. Okay. Okay, so let's check that this actually is working as a pushout. So notice the inside square commutes. Because going around this way is just F after the identity on A, and going around the other way is the identity on X after F. And, well, this is just F, and this is just F. So the square here does commute. And if we have any competitor here, and a pair of arrows, forget which blue Jason passed me earlier. Oh, this one probably. Okay, so if we have a pair of arrows from A to Q and X to Q that make this blue shifted square commute, can we find ourselves a unique arrow from X to Q that makes everything? What should that arrow be? Well, can we find any arrow from X to Q? Not having this one yet. There is this blue one, right? So what if we just try taking our unique arrow to be that blue arrow? Call this thing call this thing, let's see, G. And let's try making that thing G. Well, you can see that everything commutes that should. So you could go from A to Q. That's essential. So the A to A is just the identity. Forget about that, and that's just this map A to Q. And then you can go from A to A up to X to Q. And that's the same as doing F and then G. So why is that commutative with going from A to Q directly like that? It needs to be. So why is going from here to here to here the same as here to here to here? Yeah, that's it, very good. So remember Q, since it's a competitor, its square coming from A and X here is commutative inside. Yeah, so going along this way, and then going along F and then G is the same, right? And you see that that's the same as this F and G, right? Yeah. So it takes a little bit of staring at, but you can see that this picture does show X is a pushout of our base diagram. Okay. So since that works, and this one also works by definition. I mean, here we're just calling it the pushout of A and X. So of course it works as a pushout. So since A pushout X and simply X alone both serve as pushouts, they are canonically isomorphic. This is just a standard fact that any two things that work as a pushout have to be canonically isomorphic. So under this looser notion of being the same, we get that this holds. So this does hold. But only when equals stands for canonically isomorphic. So that's the cheap get around that we have to resort to in order to really get a strict category here. We have to use these isomorphism classes. The other identity is pretty much the same thing. You got to show that if you have X first, and then the identity on A, and you compose, once again, you just get X. And it works in exactly the same way. This is the idea.
Shouldn't you have some B's somewhere?
Sorry?
Shouldn't you have a B somewhere?
There should be, yeah. Thanks.
Several more B's. What are the two A's that are next to it?
Yeah. So, yes. Yeah, it shouldn't be now. It shouldn't be. Yeah. So you need to see that this also gives you just X, and it goes exactly the same as this. Okay, so that's all the axioms. So we have a strict category where morphisms are cospans. But, sorry, not just cospans, but canonical isomorphism classes. Actually, sorry. It's not that we want all of our so it's not that we want to treat all our morphisms as isomorphism classes here. It's just certain things that we're calling isomorphism classes. So morphisms are cospans. but it's composition that's defined up to canonical isomorphism classes. So composition and identity laws hold up to canonical isomorphism. Okay, any questions on any stuff so far? Okay, so let me talk about what a bicategory is. So basically the idea is it's a user kind of context where basically it's embracing the kind of thing that we did in this example and saying, let's no longer require that composition of things hold exactly on the nose, that they have to be exactly equal to each other, but let's just say that they need to be isomorphic to each other. And that allows you to make, well, it's a more powerful expressive kind of language because you can say that things are different in, they're different in that they're not literally exactly the same object, but they may be samey enough that you treat them as the same. Like for example, if two groups are isomorphic, they may look very different, like a group of 2x2 matrices under addition with, say, the group R4 under addition. They're exactly the same. Just take a 2x2 matrix and string out those four numbers into a four tuple, and you have the same kind of thing that R4 is made out of, right? So they're isomorphic. And groups can even be isomorphic in more than one distinct kind of way. I think in the example I just gave, they're probably canonically isomorphic in the way I described. Maybe not. Yeah, I'm not quite sure. But anyway, things can be isomorphic in more than one way. So in this kind of context, you embrace that. And it happens with these things called two morphisms. So two morphisms are going to be to morphisms just as morphisms are to objects. It's just going another layer in where you now have arrows between arrows. And these arrows are going to make a category themselves. So I should mention here these two morphisms. Themselves form categories. Okay, so this is definitely nowhere near a formal definition of bicategory, so I don't think I'm giving you that. Just kind of warming this up here. And I'll give you guys an example to play around with in your mind first. Probably the easiest example to think about is cat. The category of all small categories. Is a bicategory. It's actually an even stricter sort of thing known as a two category, but I don't want to get into the difference right now. Okay, so the objects in this bi-category are small categories. So we need to use small here because the definition of category says there needs to be sets of morphisms for any two objects. And if we don't make this requirement that we take small categories for objects, then we won't have sets of morphisms between two given categories. We'll actually have a proper class. So there's some kind of foundational issues there, but it's not that big a deal. Just if you think of your categories as being finite diagram type of categories, that's fine. So the morphisms. Well, what kind of arrow goes from one category to another? A functor. Now the two morphisms, so you wouldn't know this from the previous paragraph, but two morphisms only go between morphisms that both have a common source and target. So maybe I'll add that here. Two morphisms go between morphisms having the same source and target. Yeah, I wonder if anybody's ever studied a more general sort of thing where there are arrows going between random morphisms that don't have the same source and target. That would be a weird thing. But okay, let's say you've got one category and a functor going to another category, and you've got a second functor. Anybody know what kind of thing can pass between two functors having the same source and target categories? So I don't think John has actually brought these up in our seminar yet. No. Okay, so I think maybe a little digression is in order. So they're called natural transformations. Okay, so yeah, let's get into what is a natural transformation. So let's see, we've got a category here, another category here, and it's got a bunch of objects, arrows going between them. And same for D. I'm going to make D a more simple. Okay. Now, what does a functor do? So say we've got a functor capital F. So functors, remember, act both on the objects over here and on the arrows. And there's a compatibility requirement. And in fact, the definition of functor of categories looks pretty much exactly like the definition of a map of graphs, a morphism of graphs, which John mentioned, I think, on the first or second day or so. So what this functor does is it takes objects to objects and arrows to arrows, and the compatibility is the, this Yeah, you have to have that. So the functor condition. For any morphism, say f from A to B, so let's say this is A, this is B, this is little f. So for any morphism in your source category, you need to have that the source of the functor applied to f. So let's say here now it is capital F applied to little f, shoots it over to this arrow. So what do we need to have? The source of this guy, that's this, needs to equal what? Yes, the functor applied to the source of f, very good. And same with target. I think John abbreviated source to S and target to T. Yeah, so this is the condition for a map of graphs and also a functor, same thing. Okay, so this would have to be f of A here, and this would have to be f of E. So that's, well, actually, that's not all the conditions. You also need to have preservation of identities. So also f of the identity arrow always needs to give you the identity to the image of the object. So f of the identity of A is the identity on f of A. And you have to have composition. Preservation. Activities. Yeah, so if we call this one G now, then, looks like there's nowhere for f of g to go that will be compatible, except maybe it could go to the identity on f of b. Okay. So here's the identity to f of b. Yeah, the point is f of g circle f has to equal f of g after f of f, preservation of composition. So that'll be true with this labeling of stuff if we send little g to this identity arrow there. Okay, so that's what a functor is. Now, I claimed that the collection of all the functors from the collection of natural transformations between various functors from C to D actually forms a category itself. Oh, I haven't told you what a natural transformation is yet. Okay, I'm getting all this stuff here. Okay, so this is what a functor is. Now, what's a natural transformation? Okay. Okay, so you have a pair of functors. With the same domain target categories. How can we kind of transform one of them into the other? Yeah, so now this isn't so obvious. It should be. Trying to think rapidly off the top of my head a way to make it sound intuitive. Okay, well, what it should do is map the results of F to the results of G in a compatible way. Always this extra requirement in category theory and pretty much all over mathematics that you don't just do any old mapping, but you try to preserve any kind of structure that's lurking around in the background, right? So here's the idea. Given any morphism, little f, from A to B, we can apply the functors. To get, so we have capital F, it hits A, and it hits B. Those give a couple of objects over in D. And it hits the arrow. So we get this. And we can hit the other functor. And get another arrow. So what we want to have now is a way of filling this in so that it commutes. And this is going to be known as alpha A here. This is going to be called alpha B. Okay. So the idea is a natural transformation alpha from capital F to capital G is a family of these arrows here.
See you next week.
So it's actually a family of morphisms in our second category. You know, all of these guys, since you've hit them with the functors, live in target category. So these arrows are going to be in D. Which make the above square commute. For any morphism F. So this definition seems a little weird to everybody the first time that they see it. And maybe it'd be worthwhile doing a really baby example just to see something concrete. So let's say C is just this category. It's got two objects, an arrow between them, and of course it also has identities. And let's call that unique arrow F. Okay, and let's say, draw a G there. Right, so let's say D is just this simple category. I'll call this C, D, N. And this can be G and H. And it's also got the identity on D. The identity on E. And the identity on C. Okay, now we need a pair of functors from the first category to the second. So let's capital F and capital G. And what will capital F do? Well, let's say it just takes this morphism here and lays it on top of our top morphism here. So C is going to be big F of A. D is going to be big F of B. G is going to be big F of little f. Okay. We have no choice what to do to these morphisms with F. Identity on A has to go now to the identity on C, and identity on B has to go to the identity on D. So that's F of okay, and let's say our G brings it to the bottom one. So this is G of B. G of A equals F of A. So now what's a natural transformation from F to G? Well, it's a family of arrows in D that make a square commute. So what are the squares that we need to check with here? So for any morphism, we got to have the square commute. So let's take this morphism. Then we have, when we hit it with capital F, we're going to get well, it's going to be exactly that arrow right there. And when we hit with G, we get this bottom arrow here. Now, a natural transformation consists, well, if we actually have a natural transformation, then we would also have a pair of arrows to complete this square and make it commute. This one would be called alpha A, and this one would be called alpha B. Now, do we actually have such a pair of arrows? Well, F of A and F of A and G of A are both this point, so we could just use the identity arrow to that point there. But capital F of B and capital F of G are kind of isolated from each other. Yeah, there's no arrows between them, right? So this doesn't work. They're not naturally transformable. But if we throw in one more arrow here, call it I, say, And also demand that I is the same as, we have to demand that H is the same as doing G then I. Yeah, so I want this triangle to commute. Yeah. If we have that, then we can take alpha A to just be the identity on C in this picture, and we can take this alpha B to be I. Because then we get this commutativity, because going around this way is exactly doing this. And going around this way is just doing the identity, which does nothing, and then this. So you get the commutativity. Yeah. So not every pair of functors is going to have a natural transformation like this from one to the other, but many of them do. And an easy exercise you can do to help absorb the definition, make sure you understand it, is if alpha is a natural transformation from F to G, and beta is a natural transformation from G to H, and here capital F, G, and H are all functors with the same source and target categories. They compose to give a natural transformation from F to H. Okay, so basically the idea is if you have this natural transformation set up and then another one between G and H, these are the betas, then you can compose the alpha and betas to go all the way across. So it turns out this collection of two morphisms here for any categories C, D, there is another category where objects are functors from C to D, and morphisms are natural transformations. Okay. So I'm saying it's a full-on category. So what do we need to have a category? Well, we need some objects, functors of the objects. We need some morphisms. The natural transformations are the morphisms. And we need that they compose. Well, that's this exercise, they compose. We also need identities. So what is the identity natural transformation from F to F? Given any functor F, there's an identity natural transformation. From itself to itself. And how does that look? Well, again, we make the kind of square setup that we've been doing in the earlier examples. And what's the obvious way to fill in a couple arrows here to make a commute? Identity. Yeah. So just identity on f of A, identity on f of B. And then no matter what this morphism is, it commutes. Actually, this would be f of f. Yeah. Okay, so you can easily confirm that this thing behaves as an identity should with composition. And so that gives you a category of these functors as objects and natural transformations as morphisms. So we've also seen earlier that categories and functors makes a category as well. Right? The objects are just the categories, the functors are the morphisms. This is because functors compose and there's an identity functor, so it's very simple. So here's one category on the object and morphism level. And now I've just showed you guys that we also have a category here on the morphism and morphism of morphism level, the two morphism level. Yeah, so the idea behind a category is very much like this. You kind of have a pair of overlapping categories where the middle ground behaves as the arrows of your first category, but the objects as of your second category. This is the arrows of the first or top category, but it's the objects second bottom category. Okay, so a two category, this is also an example of a two category, and I'm going to end now. But a two category is basically this sort of thing. A bicategory is this sort of thing where there are several additional kind of complicated axioms that describe the way that things should hold only up to isomorphisms. So for example, the composition law for morphisms that ordinarily says you have to have associativity on the nose is now going to be relaxed to say you only have to have associativity up to certain isomorphisms in this level here, out of the two morphisms, and that those themselves have to obey some other kind of coherence axioms that are complicated. I was going to get into those, but time goes fast, so I think I better call it, unless anybody has any questions. Okay, thanks guys.